So I will be talking today about something which is very related to what Hongtang just told us about. I will divide my talk in two parts. One will be about inducing a nonlinear dynamics of spin with light. And then I will be talking about our most recent work, which is the coupling of optical phonons with magnon modes on top of magnetic textures. Part of this work has been done in collaboration with Hongtang, so the first part, and Florian Marquardt, and the work on magnetic textures. The hard part of the work has been done by Jasmin Graf, who's here also at the workshop, and we have collaborated also with Hans Pfeiffer, which is also at the Max Planck Institute for the Science of Light in Erlangen. And this is where I am since January as a leader of a new Max Planck research group. So a very brief outline of my talk. I will be giving a very brief introduction and motivation, since we had such a nice talk just now by Hongtang and also the talks yesterday morning. Then I will be introducing you the optomagnonic Hamiltonian, how we can get to it from a theory point of view. And I will use this Hamiltonian in a very simple example to show you how one can, in principle, control the spin dynamics of a system for the Kittel mode. And then I will be going beyond the Kittel mode and talking about magnon modes on top of magnetic textures. As an example, I will be talking about a magnetic vortex in a microdisk. So let's start with the introduction and motivation. So as we heard already this morning, so be interested in coupling magnons with photons. I just noticed that I have a different color coding than Hongtang. So my magnons are orange and my photons are blue. I hope you don't get confused. And we saw that at the microwave level, so the strong coupling has been demonstrated in this microwave cavity systems, where one can tune the resonance, the Kittel mode with the microwave mode in the cavity, and via the resonant coupling, very strong coupling and high cooperativities can be achieved. So the question is, can we couple magnons to optical photons? And I will be interested, as I said, in systems with a cavity. So as we heard today, this is of high interest, for example, for using the magnonic system as a transducer for transducing information from gigahertz regime to the telecom regime. Another kind of motivation could be also be using these systems as quantum memories. So one will write some information with the light in the system, and we will retrieve it at some later point also by reading it with light. So this is as a very brief motivation, but let's go to where does the coupling come from to optics. And actually it is due to the Faraday effect. So we have light that goes through a magnetized material, and the plane of polarization of the light will rotate as it goes through the material. The total rotation will be given by the Faraday rotation, so characteristic of the material. This is one of the reasons that makes YIG good, because this is relatively high and also combined with loss with small losses. But let's go now to the where do we get the coupling from? And this is from this expression here. So in mathematical form, we can express this Faraday effect by a modification of the electromagnetic energy in the system. This is, if you remember one of the slides from Hongtang, this is a different way of writing the coupling, but equivalent, of course, to what he showed. So this is exactly given by a modification of the permittivity of the material due to the magnetization, and which, due to the time reversal symmetry breaking, acquires an imaginary antisymmetric part. And this is what you see here. You can write it in terms of an optical spin density. So what you see here is the optical fields in this cross product form. So the easiest way to see what this is if we have circularly polarized light, then this vector will point in the plane perpendicular to the polarization. And it couples to the magnetization density in the sample. So you can see that this already at this level that there will be an inverse Faraday effect. So this optical spin density will be having an effect of a small magnetic field on this magnetization. So now we want to quantize this Hamiltonian, so we will replace, loosely speaking, we will replace the magnetization by a spin operator, and then we see from here by quantizing the electric field that we will have two photon processes. So as Hong-Tang mentioned, we'll have a parametric coupling. And from now on, I will be talking about the Kittel mode, so this mode in which all spins are locked together, and if we excite them, then we'll just start precessing all together in phase, because that will allow me to replace, as I said before, this magnetization here, to assume that it's homogeneous, to take it out of this integral, and then I will have a big macro spin that can have some dynamics on the Bloch sphere. So if we do that, we obtain a general expression for the optomagnonic coupling, which is given here. And the optomagnonic coupling coefficient in a general form for this coupling to the Kittel mode you have here. So you should, what you should get from this expression is 1. It depends on the overlap of the electric field mode functions. It is proportional to the Faraday rotation. Of course, the bigger the Faraday rotation, the better the coupling will be. And it is inversely proportional to the number of spins. So what is important is the density of magnetic excitations in the system. So, so this is what we saw earlier also in Hong-Tang's talk. So this coupling was demonstrated a couple of years ago, in which a naive sphere, which serves both as the optical cavity by these whispering gallery modes that you see here, and the host of the magnetic excitations. And the coupling was shown by seeing the sidebands at the magnonic frequencies. So what I will be telling you now is a simple example of the dynamics, of the couple dynamics of the system, in which we want to see what is the effect of the light, the coupling to this light on the spin dynamics. And for that, we take a simple Hamiltonian, which is a very simplified version of what we saw before. And here I'm writing the full Hamiltonian, which we have the photon part. We are in the rotating frame, so we can apply a driving laser to the system. And this, what you see here, is the detuning between the laser frequency and the resonant frequency of the cavity. This is the free precession of the spin. This frequency, the frequency of the Kittel mode, can be controlled by an external magnetic field. And what you see here is the coupling, so the two photons and one spin operator with a coupling constant G, which in this case we can calculate, has a simple expression. And for YIG, if we go to 1 micrometer cubed, so now we are already saying, okay, we need to go to small sizes. So if you go to micrometer cube scale, so this is 1 hertz, it is relatively, also relatively weak, but it's enhanced by, it will be enhanced by the number of photons in the cavity. So what about the dynamics of the system? In the fast cavity limit, when the photons in the cavity are much faster than the dynamics of the spin, we can actually integrate out by an analytical procedure these photons in the cavity and obtain an effective equation of motion for this macro spin. And if this equation here should be familiar to you, because it has a very similar shape to the Landau-Lifshitz-Gilbert equation of motion that you are familiar from magnetics. But notice here that now we have an effective field which will add to the external applied magnetic field, and this is optically induced, and we will also have an optically induced dissipation, which are both, because of this coupled dynamics of the system, they are nonlinear functions of the spin S. So now we can solve for the dynamics of the system using this effective equation, and I will just show you one example of what one can have. And this is in the blue detuned case, in which the frequency of the laser is larger than that of the resonance frequency of the cavity. So we are giving energy to the system. And in that sense, in that case, one can show that the optical induced dissipation actually can change sign, can even be completely negative, or in this case that I showed here, it can change sign on the Bloch sphere. And that means that in this case, because of this change of sign, what one is doing is originally the equilibrium position of our macro spin was here in the North Pole, but if we let evolve the system, as long as it is driven, the spin will go down and actually point almost to the South Pole. So basically, we are inducing a magnetic switching in the system. So we know that this is, in solid state systems, is quite complicated, because then we will start running into processes, dissipation processes that we have not considered, so the 3 and 4 Magnon processes, so like what Hong-Tan was mentioning today, so Sul instabilities. But actually, this kind of dynamic can be realized in cold atom systems, and this is an experiment in the group of Dan Steinberg-Kern of last year, in which he shows exactly this kind of behavior. So here, if the two plots are, so one is in the red detuned case, the spin is stabilized at its original equilibrium position, so it's kind of overdamped in that position. And in the opposite blue detuned regime, the spin starts getting amplified, the oscillation, and at some point it will reach, which is not shown here, but it will reach the South Pole. So that was in the first cavity limit regime. So we can also solve for the full nonlinear dynamics of the system. In that case, the nonlinear dynamics is even richer. So we have here an example in which by increasing the laser amplitude, the driving laser amplitude, and here we used again this blue detuned regime, we can go from the magnetization switching, which is not shown in this plot, to limit cycle regimes, and we can induce, we can have optically induced chaos. So this shows the richness of the system, but of course, for this we need either big couplings or a high density of photons in the cavity. So now let me go to the case of magnetic texture. So now we'll be going beyond this Kittel mode example that I was showing before. So, and as we heard now in the previous talk, so there is a problem in these optomagnonic systems, is the coupling is very weak. So, and then here I make the connection to the kind of Hamiltonian terms, coupling terms that you were seeing in Hong-Tan's talk. So in what I told you previously, I retain the spin character of the spin, so to say. But if we just restrict ourselves to small oscillation of the spin around its equilibrium position, we can replace it by a harmonic oscillator. And you see here that the coupling constant G that I talked before will be enhanced by a factor of square root of S in this case. And this G node is what I think was called G or big G in Hongtang's talk. Anyways, so yes, this is a problem which is there, and if we want to move on to interesting applications, this kind of small coupling problem has to be solved, and so some solutions will be to go to smaller systems, as we already heard, and also to better overlap of the modes. So here is it's a small sketch in which you see that if we talk about the Kittel mode trying to overlap with the whispering gallery modes in the sphere, well, this is very, the overlap is suboptimal. But so this is starting to happening. So here I took two works, very recent works from the Nakamura's group, from James Haig, who will be talking after me. So this is in the same kind of system as of this Higgs sphere, still with a homogeneous ground state of the magnetization, so saturated magnetization, but they have started to explore the optomagnonic coupling to other modes, non-homogeneous mode, beyond this Kittel mode that we were talking so far. But actually, if you go to smaller systems, you also run into a very interesting case in magnetics, which is you start getting ground states that are non-homogeneous. You start getting magnetic textures. And this is what the rest of my talk will be about, which is an example of this kind of structures that it's a well-known example, actually, which is the formation of a vortex in a micromagnetic disk. The vortex, you can see it here. So the magnetization curls in the plane of the disk, and in the middle of the disk, it will point up. This is due to a competition between exchange interactions and dipolar interactions. So the magnetization fields and the boundary of at the boundaries of the system. So these kind of vortices have been observed in many different systems. So here you have some examples of permalloy disks, some very recent example also of kind of interesting vortex structures in cobalt gadolinium pillars, and also have been observed indirectly in Higgs disks. So I will be interested in coupling to magnon modes in the presence of this vortex. And so let's just go over two basic things about this vortex configuration in this microdisk. One of them is that its position is tunable by an external magnetic field. So if I apply an external magnetic field here in the x direction, as the spins try to align with this field, they will start pushing out the vortex, so up in this sense. In this figure, they will start to push up the vortex to the rim of the disk. And the other characteristic of these vortices is that they support localized magnon modes. And the most well-known mode is the lowest energy mode, which is called the gyrotropic mode, in which the vortex, if you displace it from its equilibrium position, it will feel a restoring force, kind of a Lorentz force, because it acts perpendicular to the motion, and it will start rotating around its equilibrium position. This is a gapped mode, and it's usually in these microdisk systems in the sub-gigahertz regime. So now the question is, so if we have the ability to tune the position of this vortex and to excite these localized modes, can we couple them to whispering gallery modes in the system? So this is what I will be showing in the next few minutes, and I will be talking about two different setups that we came up with. One is a thin disk heterostructure. So thin disks are nice because one can do some analytical calculations on it to make sure that we are on the right track. And also computationally, they are quite nice to treat. So not so computational demanding. But of course, if we have a very thin YIG disk, this will not be a good optical cavity. So we propose some heterostructure in which, in this case, the simulations you will be seeing, so it's a sandwich with silicon nitride. And so the magnon modes will live in this thin YIG disk, and the optical modes can live in the whole structure. The second structure that I will be talking about is we'll be going to a full YIG disk. In this case, as it is in the sphere, we'll have that this YIG disk is both the host of the magnonic excitations and of the optical modes. But the price we pay, but also the interesting part is that then the magnetic texture is not simply 2D. They will be having a non-trivial set dependence on the height of the disk, and I will be showing you more details in the next slides. So now to what we actually do is we take this coupling Hamiltonian that I showed you before, and we treat the the magnetic part of the problem, the magnon modes in the presence of a vortex with the software MuMax 3, and we couple these to the optics. So we treat the optics with COMSOL simulations, and we calculate the coupling by putting these two things together. And if you want to know more about this, you can go to the poster of Yasmin Graf, who did all the hard work, and you can ask her all the details about how to put these two things together. So what I will be doing now in the next part is showing you some results. And this is one example of how this structure looks like. So this is a thin disk. This is the shape of the whispering gallery mode, and this is the gyrotropic mode of the vortex, which has been displaced to the rim of the disk. So you see that there is a non-trivial spatial dependence. So we can, this non-trivial spatial dependence will translate when we to the coupling. So basically, the coupling also has a spatial dependence, and to obtain the overall coupling, which we have to integrate over the whole volume. If we do that, so this is what we, one of the results that we get. And here you are seeing a plot which is how the optomagnonic coupling depends on the applied external magnetic field. So this shows you that we are able to tune the optomagnonic coupling with the applied magnetic field. So you see that the coupling has this non-monotonic dependence. And what you want to observe here is that, so in the same plot, there is the optical spin density plotted, and you see that the naive expectation that the maximum coupling will be obtained at the maximum optical spin density is not fulfilled. This is due to so this is the optical spin density evaluated at the position of the vortex. And you see when you are here, this is a very symmetric position for the vortex, but this is combined with an anti-symmetry of the magnon mode, and this gives, when you integrate over the whole volume, this turns out to cancel out. So the high symmetric point is actually gives you a 0 point, and actually effectively the magnon mode is coupling to the gradient of the optical spin density in this system. So you see where the slope is bigger, you get a larger coupling. But you see here, if you now look at the numbers, they don't look so good. So the coupling strength here is in the hertz. So we can get to 10 hertz. This is, suboptimal if you want. And the price we are paying is because now we have such localized magnon modes that we are in the opposite regime to what we were talking before. So the magnon mode is much smaller than the whispering gallery mode volume. So that's why we now went to full YIG structures. in this case. So we have the whispering gallery mode living in this microdisk, and the vortex is again displaced. But now the magnetic texture in the disk is much more interesting, if you want. So you see that the vortex kind of snakes through this through the height of the disk. So here it is already displaced, and it presents this kind of a curling structure around the vortex core. So now the magnon modes would also be more complicated, if you want, or more rich. So what you start seeing if you look at the magnon modes is that you start seeing flexural modes of this kind of string that you have of the vortex. So these are kind of like the different basically string modes of this flexural modes of this string. I don't know how to call it better. So now we go through the same procedure. We calculate the optomagnonic coupling for these modes, and you see that now the values that we get, they are much better. So we are now in the kilohertz regime for the coupling. And we start seeing that as we go up in these magnon modes, the coupling increases. So this is an example of this mode superimposed with a TE whispering gallery mode. So we can also take one of the modes and analyze the dependence on the external magnetic field. We see the same kind of behavior. So the coupling actually has this non-monotonic dependence on the magnetic field, and it's basically maximum where the gradient of the optical density is maximum. So we went through the exercise of calculating the cooperativity, so a figure of merit for these modes, and we see that single photon cooperativity for all of these is more or less the same. It's 10 to the minus 7, and if we take a maximum photon density, so to say 10 to the 5 per micrometer cube, we obtain cooperativities of 10 to the minus 2, which are an improvement, at least a theoretical improvement over the values that one sees so far. So this shows that by engineering these structures, one can obtain promising values for the coupling. So the quest is, okay, can we couple to other interesting spin wave modes that will improve the overlap with these whispering gallery modes in these structures? We show that the coupling is tunable by an external magnetic field, and there is still the question to be tackled: what is the couple dynamics between optics and magnonic excitations in this system. So this leaves me with the summary. So we started first the nonlinear induced dynamics for a Kittel mode, and I showed you some our latest results on coupling to magnonic excitations on top of magnetic textures. And thank you very much.